response modeling. First, I'm just going to give you a background, how we got our steady state operating curve and our step response and the basic stuff like that. Then I'll go on to talk about the frequency response, and then finally results and conclusions we can draw from what we had from our data. This is the level system, just a basic diagram on how it works. That's all the different tank 1, tank 2, everything that is. That's just the basic block diagram where the input motor power into the tank system and the output, which is the level of water inside tank 2, which is what we were measuring. This is our steady state operating curve. As you can see, it only really worked between 50 and 70%, and the slope of that line there is 0.86, right where it's steady state increasing. That's our transfer function that we were using, and as you can see, these are gains for our different steps from both up and down, a lot of which Blake covered in the previous presentation. Here's some more of our results. With this system, because of the way that the system works, we're looking at very high end for time values, so we actually look in terms of minutes as opposed to seconds. Sometimes the lab can take up to 30 minutes, especially with the frequency response to get enough data to even analyze anything. So the procedure for the frequency response, the first thing was we were putting a sine function in, and we could have control on the frequency, also the peak-to-peak amplitude, and the baseline motor input baseline percentage. In this, we each took a different baseline percentage, and we each used a 5% or 5% amplitude or 10% from peak to peak in terms of the values for this lab. I was running 55%, Andy at 60, and Blake at 65%. Let's make sure that we stayed within our steady state operating curve region. And the level was collected for all those. Here's the results for a sample time. This is a frequency of, as you can see, our frequency is 1,000th of a hertz. That is about in the middle of where we were able to get good data. Much higher frequency, we would get, the system takes so long to respond that you actually won't see any response, and you couldn't actually determine the delta C or a little t. So you can see capital T, which we determine the delta M for the peak to peak, the little t, and delta C. So here's some of the Bode. This is for a base of 55% and the amplitude of 5% or peak to peak 10%. Plotted on log. This is the two different results we got. One's the amplitude ratio and the other is the phase angle. Both of them look not perfectly linear on a log plot, but they are not. We can use. We should be able to model them closely. This is the equation that we use for the amplitude ratio, and then also the equation we use for the phase angle when we did our modeling for the frequency response. So here's the first one. Here's the amplitude ratio. The red line is our model. This is with the base of 55% and amplitude of 5%. As you can see, for this one, we were able to get a pretty good model at that base motor input. However, these are, as you can see, 65% and 60. As you can see, we had problems with both those. They weren't really as nicely modeled. The 60%, I know in talking with Andy, the higher frequencies, as you can see, we're getting up close to 1, and the frequency is just too high for the system. And the system's so high that the noise is, you're unable to properly determine a delta C and a little t. And so then this is here our model for our phase angle, again with the 55 and 5%. And then here's theirs as well. So looking at this, you compare the two, the 60% we weren't able to actually determine an ultimate frequency or a KCU because it didn't go to negative 180 on it. So in terms of we need to we should go back and look at maybe doing some more experiments at a lower frequency to see if we can get a better model or determine what happened. So here's some of our different values. Those are K, tau naught, T naught, tau for the models. So as you can see down here, because the 60%, you get negative 180 on the phase angle, and continue on the rest of the calculations. So in conclusion, we have to have a very low frequency for our system to be able to model it in terms of the frequency response. Higher frequencies, we can't find delta C and T values. And we also noticed in terms of the 55% and the 60% and 65% baseline, it's somewhat similar, obviously differ because of different baseline inputs. However, the 60% differ and did not sort of follow a linear pattern with the rest of the results.